move on to the keynote talk, which, as I said, is the last keynote of this year. And I'm very happy to introduce the keynoter, Mike Slessor. Mike has served as the president and chief executive officer of FormFactor since 2014, for the past 10 years, and as director since 2013. Mike served as president from 13 to 14, and as senior VP and general manager of Microprobe product group from 2012 to 13. Before joining FormFactor, he was president and CEO of Microprobe from 2008 to 12, closing the FormFactor acquisition of Microprobe. Prior to joining Microprobe, he also held various positions at KLA. Mike received his PhD in aeronautics and physics from California Institute of Technology, that's Caltech, and his bachelor from the University of British Columbia. He is a Canadian, I assume. Here we go. Very good. Welcome, Mike.
Thank you very much, Dr. Best. Thank you. Let me start with some thank yous. Thank you for the great introductions, Yvonne. And thank you for the organizing committee for reaching out. I realize this is going to be a bit of a different angle for the work most of you do every day. But my mission here is to try and teach you a little bit about Probe and where it's going, some of the things that are driving it, and then a call for collaboration at the end, because these things are getting very, very complicated in the industry. And I think if we continue to stay siloed in design, test, probe, verification, it's going to get even more challenging. Before I get into some of the details, I want to share with you some of the best advice I was given early in my career. As you just heard, I was educated as an engineer and a scientist, and so was deeply steeped in the presentation method associated with the scientific method, right? Start with your hypothesis, take people through how you did it, and then voila, at the end, tell them your conclusion. When I was at KLA, Bobby Bell, who was one of the senior vice presidents there, took me under his wing and he said, you know what, when you're going to talk to executives and accomplished people, tell them what you're going to tell them. Right? Don't walk them through the entire chain of reasoning. Tell them what you're going to tell them. So I'm going to start by telling you what I'm going to tell you. Probe is becoming more important for several reasons. One is pretty obvious. There's significant value in moving test and screening upstream as close to the wafer fab as you can. This, often referred to as shift left, which you'll see in a flow chart in a second, allows you to do several things, right? One allows you to screen out bad material before it goes into assembly. So you're not incurring costs on die that aren't going to work anyway, or at least aren't going to work on the performance level that they should. The other thing this drives is a faster feedback loop to the fab for yield improvement. And as process node ramps accelerate, as device ramps accelerate, this is becoming more important as well, driving a shorter time to results for yield improvement. But the real theme of what I'm going to share with you today is Probe is becoming more important because of advanced packaging. Chiplets, 2.5 3D integration, as you see down the bottom, I'm going to use these all interchangeably. But the idea of building chips out of chiplets or subcomponents instead of a monolithic piece of silicon has a surprisingly profound effect on test and probe and pushes us much closer towards known good die, as you'll see. This is also impacting what we generically call complexity at wafer test. Essentially, the specs required to do wafer test, things like speeds are going up, temperature ranges are going up, voltage and current stress being applied at sort, where there were really only final test items before, or burn-in items. The other nuance we'll get into, as is with advanced packaging, there are some very, very aggressive pitch scaling requirements associated with how these chiplets are attached to each other in the advanced package. And that has a pretty profound effect on probe, mostly because our lives in probe have been involved with connecting through the packaging interconnects. That works just fine for wire bonds, big pitches, big pads, even flip chip bumps down to 75-ish microns. That's worked really well for the industry. When you go to something like copper-to-copper hybrid bonding and the pitches get to 5 microns, 10 microns, it's a whole different game. And we'll talk about how the industry is dealing with that. I'll give you a couple of examples of how really high-performance compute and AI is driving a lot of these requirements as a theme that goes through our product roadmaps. And then hopefully inspire you a little bit with how we're enabling, not in volume production, but things like co-package optics and quantum computing. So let's start, just to make sure everybody's on the same page. What is wafer probe and why is it important? So I've borrowed this test flow slide that was presented last year at the Semiconductor Wafer Test Workshop, because I think it's a good description of essentially the back end, right, with a focus on test. The important thing to note here, you can see all these test insertions, right? Final test everybody's familiar with, burn-in system level test becoming a much bigger part of overall test spending. Sort or probe, again, I'll use those interchangeably, is the only opportunity you have prior to assembly to see how good the die are. And that has really profound implications on then the downstream assembly processes and the costs you incur in those. To do probe, you typically require 3 basic subcomponents, 3 basic pieces of equipment. One, which I'm sure most of you are familiar with, automated test equipment. These are the testers built by people like Teradyne, Advantest, Cohu, that drive vectors into the part and collect a ton of information on how each die is performing. You need a prober to handle the wafer or the die and move it around, control the temperature. It's sort of the physical positioning mechanism in this. And the element I'm going to mostly focus on here, because it's FormFactor's largest business, is the probe card. This is the interface between the ATE and the chip on the wafer. Think of it as a connector. Now that's a vast oversimplification, as you'll see, but that's its basic role, is to connect ATE to the device and make sure that connection is reliable, cost-effective, low impedance at a wide variety of frequencies. But again, think about it as a connector. Why do people do wafer probe? So this is a little bit qualitative, but it'll motivate some of the examples we go through in the rest of the talk. The chart I have here, so the horizontal axis is the cost of post-assembly yield loss. Essentially the cost of scrapping a die at final test or system level test after I've done all this work in assembling it either into a package with itself, with one die, or a package, and this gets really interesting, with multiple die or chiplets. The vertical axis is essentially the inverse of yield coming into that assembly process, right? So if I had, and it's 1 minus, so that things go up and to the right, and everything looks nice in this cartoon chart. If I were really being rigorous, it would be turned upside down, and things would go down and to the left. But our marketing people didn't like that, so we have this axis. When you have low incoming yields to assembly, low native incoming yields to assembly, and a high cost of loss at the end of assembly, at final test, you're up and to the right. You're in this scenario like we have today with GPUs packaged together with high bandwidth memory in things like TSMC's CoWoS process. There is a very high return on doing wafer sort for those individual components, the GPUs, the HBM, even the interposers themselves. The opposite end of the spectrum is something like, a MOSFET or a simple analog chip. Yields are very high. Again, the vertical axis is 1 minus yield. And the packages are pretty cheap, the die are pretty cheap. It makes no economic sense to do wafer tests, to buy ATE, these fancy probe cards, wafer handler. Customers just essentially build the parts, test them at final, and scrap out whatever doesn't work. And that tends to be a very rational way to do things. All right, so now that I've told you sort of what wafer probe is, how does FormFactor fit into this? And I promise this will be the only sort of quasi-ad in the talk, but I wanted to at least motivate why we're here today. Pretty broad-based company. We're mostly known for probe cards, and we'll come back to that in a moment. But over the years, we've diversified the business to have a presence in engineering lab test through essentially the purchase of Cascade Microtech about 10 years ago. And that got us way upstream into customer R&D and development. More characterization than the wafer sort use cases I talked about, but gives us wonderful insight. And as you'll see when we talk about co-packaged optics and quantum computing, some really interesting vantage points in enabling next generation industry trends. But returning to the right-hand end of the slide in production probe cards, this is about 80% of our business, 80% of a $250 million of annual revenue. We lead in overall market share in probe cards and are probably the only provider that really has a leadership position in both memory and logic. And that's created some interesting opportunities for us as you see combinations like this GPU HBM advanced package. All right, so let's now get into some of the details of a probe card. As I told you, it's basically a connector, but here's some of the complexity of that connector. This is a state-of-the-art logic or SoC probe card. Tests 16 die at once, comprised of about 80,000 individual probes that are right around this 75 micron pitch. So we'll start at the left, right, with sort of the thing that you see when you see a probe card. It's a great big printed circuit board, about somewhere around twice the size of a basketball. That size is driven mostly by the interface to the ATE, the size of the test head, the connector layout, that kind of thing. But as we zoom into the center, which is the probe head, you start to see some of the complexity. And you see a collection of 4+ die here on the 16 die probe card. Each of those probes, the 80,000 probes, maps to an individual bump that you're going to make an electrical connection to, either a power, a ground, or an I/O. If we zoom in even further, right, so basketball scale, pencil scale, human hair scale, you can see what each of these probes look like. So, here's where I talk about the complexity. These are 80,000 individual probes on this card, all produced by a MEMS-like process. And they have to basically carry, around an amp of current. They have to live for millions of touchdowns, have very stable contact resistance, and in some cases operate, as you'll see, at fairly high frequencies. This is, when we look at where things were 50-odd years ago, we were nowhere close to this. You had maybe, 5,000 probes per probe card was considered a big card. But the drive for complexity, right, more complex die, higher performance die, and then lower cost of test, so higher parallelism, because that's by far the key driver of lowering cost of test, you see some pretty significant increases in complexity. So that's logic state of the art. Here's DRAM state of the art. A very different kind of approach, but still using the same fundamental technology building blocks. In DRAM, rather than testing 6 die at once, you're testing the whole wafer at once. Every die on the wafer tested in parallel. One, because you can do it. I was on a panel with Phil Bird yesterday, and he talked about, from Micron, he talked about DRAM having pretty shallow vector depth. Well, here's one of the advantages that gives you compared to SoC. You can test every die on the wafer at once, and that has wonderful cost of ownership. But it creates a pretty complex interface to the wafer. Again, a little bit bigger than a basketball. Around 2 times the probes, 150,000. We've even shipped cards with 200,000 probes for development. You see that sort of in the middle at the pencil scale. And then at the individual probe, again with a human hair for reference, you see these MEMS probes, which are very complex microstructures, and you get a better flavor of it here. There's about 6 or 7 different materials in each of these probes. They're like microcomposites, right? So you have to essentially have a great deal of compliance to accommodate all the topography changes on the wafer. And that's what makes this tricky, right? These are not just connectors that plug into the wafer. They need a great deal of compliance to basically accommodate the topography that happens in a test cell and be robust enough, right? Again, to last millions of touchdowns, carry an amp of current, all that kind of thing. So that gives you, I hope, a sense of what state-of-the-art probe cards look like. Now let's talk about what's happening in the business and the economics of this, and me sort of motivate the probe is becoming more important. The chart here, 2 axes. One, well, the horizontal axis, obviously over time, you know, the last 15 years or so. The left, which are the bars, is the total dollars spent on semiconductor probe cards. You know, around, let's call it today, around a little over $2 billion. The more interesting piece of this chart is the line, and that's intensity, which you can see my definition down the bottom, but it's probe card sales normalized by total semiconductor revenue. And you can see that's taken a rather dramatic step up. I magnified the axis a little bit, but you can see the trend is clear. Probe card spending or intensity normalized by semiconductor revenues gone up by about 10% starting in the 2018-2019 timeframe. That's for the reasons we talked about in the first slide. One, the desire and capability to shift test content left to wafer probe. 2, the onset of advanced packaging and the beginning of the adoption of chiplet and 3D packaging strategies that, as you'll see in a second, almost require known good die to be economically viable. One number I want you to remember here is down in the lower right. So today we're running at, let's call it in round numbers, 0.4%. So 0.4% of total semiconductor revenues spent on probe cards. We'll come back to that number in a minute when we talk about HBM, high bandwidth memory. Okay, so here's another slide I borrowed from Hamid Azimi. And it's getting a little bit old, but I think it's the most straightforward and compelling explanation of why test is important for advanced packaging. The graph on the right is based on some very simple arithmetic and just plots essentially, you know, the number of escapes you have out of wafer yield, so the gap to known good die, the number of bad die you have coming into assembly, against the final aggregate yield, essentially the final test yield, for a variety of chiplet configurations. A single die, or 2 die, 4 die, 8 die, 16 die. And you can see from this, not surprisingly, even at a fixed gap to known good die, let's pick a percent, right? A percent of the die coming through wafer test actually make it through, but are not good because of gaps in test coverage, because of sampling problems, whatever. If you got 1% of your chiplets going into the assembly process that are not going to work, you know, for a single die, that's not a big deal. All you're doing is throwing out then the cost of that die plus the cost to package it. But you can see that, you know, take the most extreme example on this chart, a 16 die stack, right? That has really profound implications, right? Then your yield is only going to be 85%. And this is what's driving your final yield of the entire stack. And this is what's driving the increase in test intensity and test capability. To drive this escapees out of wafer test down so that you don't end up packaging bad chiplets with a whole bunch of good chiplets. You know, in that bottom line, one bad chiplet with 15 good chiplets means 85%, statistically 85% final test yield. On the right, a more subtle but also very interesting implication of chiplets. And it's kind of I think of it as a lowest common denominator principle. If you're going to package different pieces of silicon together, the matching of their performance levels is pretty important, right? You can imagine that if you're packaging 3 high performance die together, as in this example, with 1 lower performance, the system's only going to operate as good as its weakest link. And so that's also driving up test complexity to do things like at-speed test at the wafer level, to do components of system-level test at the wafer level, where there's some degree of memory and other active circuitry on the probe card, at least for a SoC die test, to really exercise all the different failure modes and make sure that you have matching across the overall chiplet stack and each component. So here's an example. We'll take that chart, it's over on the right, and talk about one of these examples of the silicon driving generative AI, the things at the heart of generative AI. So this, an example I took from Fubon Research. They're associated with Jefferies, the investment bank. But it shows kind of the layout at a very high level of the AMD MI300X. They're offering for combined GPU high bandwidth memory. So, you see 9 5-nanometer chiplets, 4 6-nanometer chiplets, and 8 HBM stacks. And we'll get into the HBM detail in a second. But go back to our previous example, right? If you're taking these relatively advanced node chips and bringing them together, you better have pretty high confidence they're going to work, or the probability, going back to our last chart, of a single chiplet taking down all of the other chips in this package is pretty high. Taking a look at HBM for a moment, high bandwidth memory is one of the key enablers of this very rapid computation on these GPU stacks. 2 examples on the right, and these are superimposed on Hamid's chart. The first and second generation of HBM were mostly 4 high DRAM stacks. So a base die, then attached together with 4 DRAM die, using advanced packaging techniques, typically like through silicon vias, thermocompression bonding. People are looking at hybrid bonding, but connecting these die together to get the very high bandwidth that's needed to keep pace with the GPU computation. So 4 die sits on the second line in Hamid's curve, right? And you can see if I have a % escape out of wafer test, so a 1% gap to truly known good die, I sit at 96% aggregate yield. That's maybe tolerable, although a percentage point of yield is nothing to sneeze at, given the cost of today's industry. If I go to a 16 high stack, however, the math gets pretty sobering, right? And this is same 1% gap to KGD. And this is a real example, right? HBM4 under development right now by all the major DRAM manufacturers, being pushed very, very hard by customers like NVIDIA and AMD. If you think about just the implications of going to a 16 high stack versus a 4 high stack, everything else being equal, right? That drives a 10% yield gap for the final assembler, right? So that's one of the reasons why there's this push towards higher and higher test intensity at wafer probe to drive the escapees at a wafer test down and get closer to known good die. Remember, I asked you to think about this 0.4% probe card spending intensity industry-wide. There was a recent report from TD Cowen, another investment bank, because they're acutely interested in understanding the entire artificial intelligence supply chain. They recently published that for HBM, probe card intensity is 0.9%. And as one of the key suppliers in HBM probe cards, that number's about right? Pretty consistent with our estimates. That's double the industry-wide trend, right? Even with the climb up we saw, right, to 0.4%, right, customers are spending almost twice as much on HBM probe as they do on anything else probe or the broader industry probe. So there's another example of how advanced packaging driving this increase in test intensity. As we then think about the implication of advanced packaging, and this is a chart from Besi's investor presentation. Besi, an assembly tool company, so they build essentially the bonders that stack all these die together, and so have wonderful insight into all the different die integration methods that are at work in the industry today. And this goes back to my comment about the contacted pitch. Essentially, the pitch is getting more and more challenging, right? At least if you're going to use the packaging interconnects, the bumps or wire bond pads or different structures that are going to be used to attach to the package. This gives you a sense of that evolution. And there's two places where I want to focus on. Remembering that probe has typically been done through these packaging contacts. And the fourth line from the bottom, contact density. For wire bond, easy, right? Big pads, spaced far apart, easy to contact. And this has always been the way, for example, microcontroller test is done, or DRAM test. You use the bond pads as the contact points. You gotta be a little bit careful with where you touch them and that sort of thing, but it's not an insurmountable challenge. Move through things like flip chip. So flip chip, and I'll connect this to the chart on the right in a second, lives at somewhere around, at least in the most challenging configurations, this 75 micron pitch I referred to. Our example of a state-of-the-art probe card in SoC or logic, right around this level. And that's something that could be done fairly effectively, fairly cost effectively. But fast forward to something like hybrid bonding. So this is copper to copper bonding, very, very high densities. You see orders of magnitude higher than flip chip. Hybrid bonding, no question, going to be one of the ways that advanced packaging gets enabled. It's not in really high volume use at this point. There's a couple of applications where it is. I think it's certainly public knowledge and fairly common knowledge that some of the latest processor roadmaps, data center processor roadmaps from both Intel and AMD employ hybrid bonding to attach the different die together. So it is in use in pilot production. Now over to the chart on the right, where I said at pitches smaller than flip chip pitches, things get hard, right? And here's why. So pitch, obviously, the spacing between probes on the horizontal axis, and a very important parameter to a probe card manufacturer, a test engineer, something called current carrying capability. You can imagine those pictures of probes I showed you that are about the size of a human hair. If you drive too much current through them, they go poof. They act like a fuse. And there's different ways to mitigate that. Things like current clamps and things like clever routing and that kind of thing. But fundamentally, it seems to always happen. Either there's a current spike that happens faster than the clamps can adapt to. This is one of the reasons why we employ hundreds of people around the world who repair probe cards in the region, Taiwan, Korea, where they're used. Because probes are always getting damaged and always burned. So 75 micron pitch, and these are two probe designs, both utilizing the MEMS technology I referred to. All we're doing is scaling them in pitch. You see, not surprisingly, as I go to smaller pitches and therefore smaller cross-sections of the probe, right, it's simple math, right? If I have 10 micron pitch, I can't have a probe that's 40 microns across, otherwise it's going to touch two bumps at once. As I go from 75 micron pitch, I go to something usable. Around an amp seems to be a threshold that really creates reasonable production robustness. If I go to hybrid bonding pitches of a few microns, I essentially have no current carrying capability. I mean, we're talking about maybe 100 milliamps, right? And so there's a robustness problem if I want to stick with this paradigm of contacting, interfacing through the pitches that are going to be the package interconnects. And that's causing some very interesting choices to be made across the industry. You can see, we'll see the example with HBM in a second. But with those dramatically shrinking pitches, people, customers, manufacturers are resorting to some other techniques. Maybe dropping dummy pads in between the hybrid bonding contacts, using those as dedicated test contacts, and then relying on some degree of DFT. There are cases on customer roadmaps, however, where that's not possible. There's not enough spare area on the die to drop in a test contact that is easier to probe, simpler to probe than the packaging contact. Now, both of these things can be done, we'll see on the next slide. But a real economic choice. Remember, the reason people are doing probe is to screen out bad die and to have a significant ROI associated with that activity. If you build a super complex probe card that tests every bump on one of these hybrid bond devices, that's going to be really expensive, right? And so you've undone the very thing you're trying to accomplish by creating very high cost of wafer sort that may not have any ROI. Having said that, in characterization and development, there are many cases where we and our competitors do build probe cards that that contact every or a majority of the hybrid bonding bump. Again, they're just very complex, and as you can see from the CCC chart, not very robust. Okay, so let's take a look at a real example. And I want to come back to HBM, right? Again, high bandwidth memory or HBM attached to all these GPUs. You got two choices here. Just to give you a sense of what you're dealing with, and this, I have pictures of HBM3, but I'm not really allowed to share them. So this is an HBM2 paper from a while ago, but the principle holds. You see the micro bumps that the different DRAM stacks, different DRAM die are going to be used to attach each other over in the SEMs on the right. And so you've got these things, they're about 20, 30 microns in diameter, 55 micron pitch for this HBM2 example. Over on the right, a cartoon of the top-down view of those. So you've got this sea of micro bumps, and then interspersed, you've got these test pads, right? So I've got two choices here. Do I probe the micro bumps, or do I put these test pads in and then use those as the interface for probe, decoupling the packaging contacts from the test contacts? And there's different reasons, there's different choices, as you can see in the table down the bottom, to do both. Let's start with the micro bump one. I think the advantages there are obvious, right? Clearly gives you the highest possible, if not test content, test access. And you don't chew up any silicon real estate or packaging real estate dropping in these test pads. So you can use all of the space for these die-to-die interconnects, improving PI, PDN, all kinds of advantages associated with that. The cons associated with that are what I talked about. This is a super complex probe card and probe methodology. And it will increase cost. No ifs, no ands, no buts, right? It's a less robust probe card. Remember the CCC chart I showed you. But also just simple things, if there's a particle around, right? A probe with sort of a 10 micron pitch probe is a lot less robust than an 80 micron pitch probe. The other thing that, outside the purview of this conference, but a big deal for manufacturers overall, is assembly integration people get really, really picky about what touches their bumps, right? And for things like copper-to-copper interconnects and hybrid bonding, any kind of contamination drives that attach yield down. So there's some disadvantages in probing, physically contacting these microbumps. Let's move to the test pad scenario, which, to cut to the chase, is what's being used for high volume manufacturing of HBM3 and HBM3E today. You can use, remember the memory probe card example I showed you, the DRAM probe card example I showed you that tests the whole wafer at once, really robust, you can use that exact same technology. Now, we drive speed up a little bit, and so maybe there's a trade-off between testing the whole wafer at once, at least at speed, maybe slightly lower parallelism, but way higher parallelism than the microbump case. And, you know, hundreds of millions, maybe even, you know, billions of MEMS probes have been shipped over the years associated with this technology. So, robust, known, production proven, pretty low risk. The downsides are, of course, you don't get nearly the test coverage, right? You got to connect this test pad and then rely on some degree of DFT. The other one, and this may be just a dead showstopper, is those pads, as you can see in the cartoon, consume a pretty significant amount of area. And if the design of the chip requires maximum degree of connectivity between, for example, the layers of HBM, then this becomes a real problem, right? You just don't have room to drop in these test pads. But at least for HBM3 and HBM3, that's the way the industry is working today. Again, you know, in early development and characterization, because of the need for very high fidelity characterization and sort, we do build cards and help customers do microbump tests. But by the time it gets to high volume production, you've backed off to this other more cost-effective way through the test pads. All right, I'm now going to shift gears a little bit, and hoping, yeah, we're going to have about 10 minutes for questions. That's good. Shifting gears a little bit, remember my chart that was the ad of FormFactor, going upstream and talking about what we're doing, not just to enable production today and things like GPUs with HBM, but what are some of the other things that Probe is helping enable? One of the more exciting ones is co-packaged optics. And to put this into context for you, you know, the headline on the right, take a step back. Who would have thought a decade ago that the hyperscalers, maybe they weren't called the hyperscalers then, but let's call it Microsoft, would be getting into the nuclear power business? That's crazy, right? But it's driven by the power consumption, the energy consumption associated with these data centers. And to put that into perspective, you see the interesting quote here. If all the Google searches use Gen AI engines like ChatGPT, that's as much electricity as the entire country of Ireland uses. So these are big, big, big problems, right? As you can see from some of those statements. So what's one of the solutions? Here's a slide that was presented by TSMC and then reproduced on AnandTech, one of these websites. But you can see what co-packaged optics offers is power reduction. Power reduction at higher speed. And so that's a very compelling, if not solution, at least offset to hyperscalers' need to get into the nuclear power business. And so, you know, still well in front of production, right? We're in early pilot production. Think of it as like a wafer per day, right? A wafer per week with some of the leading manufacturers. But one of the things we've tried to do is expand our probing roadmap, and I know this is true for some of our competitors as well, to not just probe electrically, like we've talked about all the way up to now in this, but also optically, and then do them together, because these are obviously hybrid devices. They're electro-optical devices. That's something that requires a whole new way of thinking about probing, right? And the interfaces, we still use the same kind of interfaces for the electrical part of the equation, but it's required us to invent entirely new interfaces for the optical side of the interface. So an interesting way, again, probe, not just electrical probe, helping enable the industry move forward. The final one I'll leave you with is one that's near and dear to my heart. As you remember from my bio, I studied aeronautics and physics at Caltech. And so it was after Richard Feynman had left, but his shadow still hung very heavy over the Institute. In fact, my PhD advisor had Feynman on his PhD committee. So kind of a small family place. And, you know, one of the things that's so compelling about quantum computing is best captured, I think, in this quote from Feynman that maybe most of you have seen. If you're going to simulate nature, you better do it quantum mechanically. And that turns out to be a bit of a stretch for a digital computer, a von Neumann computer. You can build models, and right, it can be done for sure, but it's kind of a square peg in a round hole when you think about it from solving the fundamental problem. If you had a quantum computer that behaves quantum mechanically, boy, it's got to be a much more natural fit to do things like molecular simulations, drug discovery. The one that's maybe a little counterintuitive here is cryptography. But it turns out that quantum computers are very good at factoring large prime numbers, and that's the core of cryptography. That's where most of the funding's coming from, because you imagine the governments around the world are really interested in how to generate codes and break codes. And so that's why this is such an active area of investment right now. But it's still pretty early, right? A qubit, which is the analog of the transistor, a qubit to a quantum computer is a transistor to a digital computer. Putting those together into a usable, scalable system that doesn't have a lot of computational errors associated with it is tricky business. And so it's still, I think it's fair to characterize by and large in research. There's people like IBM, like Google, who are close to commercializing. There was a really cool 60 Minutes, for those of you who live in the US, a few months ago, maybe a year ago, that you can go find on the web, that took inside, I think it was an IBM lab, and really gave an understanding of where quantum computing is. The challenge here is these things only work really close to absolute zero. And so, you see some nice pictures here. But one of the things we've been working with partners on is the ability to probe and contact the device at close to absolute zero and not disturb it, right? So you can imagine things as subtle as current running through a probe that generates a magnetic field, screws the whole thing up. So you have to have no magnetic field, right, associated with either the probe, the current it carries, or the environment. And that drives some interesting requirement. You can see an example here. Again, we're in characterization, but an example here where we work together with MIT Lincoln Labs using the tool you see on the right, which takes a whole 200 or 300 millimeter wafer and rapidly characterizes it for the key parameters in the qubits. All right, with that, I'm going to wrap up by showing what's happened to our industry with this increase in complexity and increase of spending. This over a longer time frame. I'd taken you through a 15-year horizon. This, the last quarter century. One of the things that's happened is there's been significant consolidation. And as you work your way through, it's natural that that happens. FormFactor itself has been part of that. To meet these requirements and have the R&D budgets and the scale required to meet these challenges is a daunting task. And so what's that's caused? So that people have profitable business models and can still invest in the R&D, that's caused a lot of consolidation among probe card manufacturers, among ATE manufacturers, you can see them all here, and among prober manufacturers. I don't know that that's going to continue, because we're now in a state where in each served segment, there's two viable leading suppliers. Customers need two suppliers. They're never, unless you're ASML, they're never going to sole source with you, right? So that's a healthy industry structure, but it probably doesn't need to go too much beyond this. All right, with that, we'll wrap up and leave a couple of minutes for questions. I told you almost all of this at the start, right? So I won't read it to you again. But I hope I've taught you something about why probe is important, motivated, why customers are spending more money on it, not just more money from a growth standpoint, but a larger percentage of overall semiconductor revenue, and then some of the challenges that face us. These challenges are difficult, right? And I think what I want to leave you with is a call for less silos and more collaboration. By the time we get the requirements to build a probe card, the die layout set, you got to go contact these bumps. There's no negotiation, flexibility, co-optimization of this, right? And I think the result of that is we build really complex and really expensive things, right? Probe cards used to be a few $1,000s, right? That DRAM probe card example I showed you can go as high as $300,000 each. Now, there's still ROI associated with that, otherwise customers wouldn't buy it. But, you know, if we're going to solve some of these challenges as an industry, I think there needs to be much more system-level thought from design, bump layout, test strategies, all the way through probe, so that there's some co-optimization for cost. Because again, remember, this is all about cost reduction and ROI of screening out bad die and making sure that we're not scrapping very, very expensive parts at the end of the line. Thank you very much. Questions? I think there's 2 mics, right?
Yeah, question. Yeah, this side, sir.
Yes, Stefan.
Questions, hi.
Yeah.
Interesting presentation. I work for Renaissance Electronics. We have multi-die products coming up. Many of these are very applicable. The concern is this. Right now, say a single die, a package die, the cost of test, I'm not talking about DFT, going into silicon, just cost of test as a percentage of the packaged product. And if you extrapolate that to a multi-die,
Yep.
this, with all the capabilities you are talking about, it looks like an order of magnitude higher. What can we do to bring it down?
Yeah.
The expectation from the management, you have to keep whatever that percentage on single die had to keep the same.
Right. Yeah. 2 answers for you, right? One is the bottom bullet here, right? By the time we get to, okay, here's the die layout, here's what you need to test, right? It's basically fixed, right? We're publicly traded. You can go look at my P&L. I got 45% gross margins, right? I'm not kicking it out of the park like some other companies are. So, and you look at my competitors, same kind of thing. These are rational business models that then allow. So it's not going to come from squeezing probe cards and ATE and different things tighter. It's going to become more thoughtful, going to come from more thoughtful optimization of design, what needs to be tested, and then building the interfaces and the ATE around it. That's my view. The other simple knob, right, is, well, just improve wafer yield. Now, I spent a bunch of time in the front end. I know it's not that simple. But.
You mean increasing revenue means you have to increase the product cost? I mean, product price,
Yeah.
right?
Yeah.
That's out of the question. If it is, say, a ballpark figure is 5% of the is test cost. Is it realistic for a multi-die scenario? Can you keep it still at 5%? And of this, this is something we need to think about, how to do this.
Again, something we need to think about.
Yeah, that's what I meant.
You hand me a set of requirements, I need to have a viable business model in producing those and generate a profit, right? Yes, I'm at the end of the line, but handed a set of constraints that drive a very expensive probe interface, there's not a lot of fundamental cost reduction available in the paradigm we operate today.
And maybe more provisions could be gone for test purposes right in the silicon?
Sorry?
More DFT methods can go into the silicon.
Yeah, but silicon's not cheap either.
Yeah.
Yeah. But yeah, certainly that's one of the alternatives.
Yeah.
Okay.
Thank you.
Thank you.
Okay, thanks. Steve?
Very nice. You covered some of the trends in energy per bit and current. What about voltage? For a lot of automotive parts and other power solar panels and so on, we're seeing more and more chips addressing higher voltage. What kind of trends do you see on handling higher voltage and probing?
Yeah. We don't see it a lot in the production business, again, because yields tend to be pretty high for those kind of parts. Where we do have visibility to it is in this engineering systems business I showed you, where we build high voltage probers primarily for characterization. But some of the things like silicon carbide, gallium arsenide, the move to those new materials are requiring quite a bit of characterization by those tools. I think those kind of applications, you think about the range of voltages we have to deal with, right? We as an industry, not we FormFactor. From voltages that are going down in high-end logic, right, to voltages, now you're talking about hundreds and hundreds of volts for some of these MOSFETs. And so yes, they're moving up. Yes, they require more characterization, but there's not a lot of our business that's exposed to that. So I don't have as good as insight there as I do towards the high-end logic, high-end memory end.
Thanks, Steve. Please.
Hello, Mike. This is a good speech. And customer is pursuing the most cost-effective testing, but the per cost is become higher due to the high pin count. And besides to tracing the higher power reason, is there any limitation of the pin count growth? Maybe it will be saturated and constrained by the tester capability or the per size, or if there are any other factor to have this constraint?
Well, I won't go back. Probe counts are going up, right? But if you look at ATE roadmaps, right, pin counts, channel counts, capability are going up as well, purely because it makes economic sense to go to higher and higher parallelism. Now, we're at a limit in DRAM, right, of testing the whole wafer at once. There's some subtleties associated with that. But in logic, you're only testing 16 die at once. And so there's room to grow there. But to your point, right, we need to be in lockstep with the tester manufacturers, right, and our customers to make sure, one, all of this stuff works together. And that's one of the calls for the open ecosystem to work together. But so far, it's always been the case and continues to be the case on most people's roadmaps that more probes, higher parallelism is a better economic choice. Even though it results in much higher prices for the tester, the probe card, that sort of thing, there's still better ROI associated with it.
Okay. And I have a second question is that, and also for the HPC probing, that we induce a lot of high tip burn rate, right? So how to make sure our have the shorter MTTR or code repair cycle time, or how we can secure higher MTBF?
Yeah.
Yeah.
You're talking about probe burn rates in production.
Yeah.
So remember that CCC chart I showed, right? One of the very basic ways to improve current carrying capability and therefore reducing burn rate is to probe at larger pitches. So one of the techniques used for microbumps for powers and grounds, which is where burning is a problem, is you actually don't touch the individual bumps, you touch 4 bumps or 6 bumps or 8 bumps at once so that you have a much larger probe to do that. The other thing, and this starts to get into the technical minutia, there's things you can do in the rest of the probe card to distribute the current before it goes all the way up the probe, right? So structures that then couple the power nets together very close to the wafer, and that turns out to help burning quite a bit, because it's usually 1 or 2 bumps in the net that are causing the problem.
Okay. Thank you.
You're welcome.
Okay, we seem to have exhausted the questions and just on time. Thank you so much, Mike.
Thank you very much.
Thank you.
Thanks, everyone.
Thank you all. Short break. We're starting the sessions in 30 minutes. Okay? Thank you. It's your laptop.